Hi there.
Hey. Hi.
That was the sound of the Science and Eternity team, and this is the Science and Eternity podcast, where we explore the relationship between groundbreaking science and the human experience. This episode, we're looking at the nature of time and how it can be quite confusing, and how mystery in science can lead us to some very interesting existential questions. I'm Tom Cousins, your presenter, and joining me today is Professor David Wilkinson, a physicist, media contributor, and writer on people like Stephen Hawking. Would you mind introducing yourself, David, and why you're so interested in physics?
Well, I never used to be interested in physics. When I was at school, I thought physics was quite a predictable and quite boring thing. You used to push wooden trolleys down benches and you'd know the answer to questions because you would have looked it up in the previous year's books that people had done. But what happened to me was that I decided to go to university to study physics. And to be honest, that wasn't because I was fascinated by the subject. It was because I was pretty good at cricket and I knew I wanted to play cricket at university. But I found myself at Durham University not as good at cricket as I thought I was, but also beginning to study physics. And at university, you begin to study different types of physics. Quantum theory and relativity were the courses in the first term of physics at Durham. And this was mind-blowing. It introduced a whole new concept, not just to physics, but to the world as it is.
I think it's really interesting that cricket was your starting point for an interest in science. I think this episode we're exploring mystery, and in particular it interests me that it's not necessarily that scientists discover their beliefs or their interest in mystery from their science. It's often that they bring it to their science as well. And I asked the question, what has your science done for your understanding of mystery?
Science is a fascinating thing. It allows you to ask questions of that which seems to be mysterious in the universe. And so questions about the nature of stars and galaxies and the universe itself, which became my interest as a professional astrophysicist. And it allows you to disclose some of the questions that you thought were mysterious. But at the same time, it opens up lots of other questions. So you begin to open a door just a little bit, and you find a whole flood of questions then come through, and a whole series of doors again. Some of which you can open quite easily, and you can find answers to. Some of which are really quite difficult to get open, and some of which to this day remain closed to me because I haven't found a way of opening them. But it also, in a more fundamental way, says that the universe is far different from our everyday experience, such as playing cricket. Cricket works by being a predictable sport. That is, when a cricket ball moves towards you as a batsman, you have to judge where it is and how it's moving. You can judge that pretty well at an everyday level, at least if you're a good batsman, that is. Whereas the type of physics that we deal with, stars and galaxies, the universe itself, is almost completely different. It has different laws to it. It has different understandings to it. Our everyday concepts such as space and time, predictability, all of that becomes a very small, very, very small part of what the universe is actually like. And that's the excitement for me of physics, that it takes us out of the everyday into the universe as it really is.
I think perhaps what I find so fascinating about, as you're talking about mystery in the universe and in particular our perception of time, as you play cricket, you understand how the physics of the ball, right? When it comes at you, you know roughly how it's going to behave, apart from those iffy spin bowlers. And I think the same is true with time. Last episode we explored how our experience of time is that of decay. We remember things in a more ordered state than they are currently. There is this arrow of time that seems inevitable. Our experience of time is chronological, like a ticking clock.
Absolutely.
On the other hand, we have this far-off concept of time being distorted and manipulated. It seems really sci-fi, and often the only way we can actually explore it is creatively. We have films, there are so many films now exploring the very nature of time, but it seems so sci-fi to us. How do we even begin to understand the true nature of time?
Well, it's not too much sci-fi in the sense that we've been understanding time at least for 100 years or so in a very different way. Now, the predictability comes from Isaac Newton. who apparently, according to urban legend, was hit on the head by an apple. And out of that, he talked about the universe as a clock, a clockwork mechanism, deterministic, predictable. Wherever you were in the universe, that would be the case. The beginning of the 20th century, Albert Einstein came along and said, I want to think about time in a different kind of way. And what he gave us was a picture not of just one time at all places in the universe, but more like time as a river, where you have different rates of flow of time in this overall thing that we call time. Now, this was quite bizarre. So, for instance, time flows differently depending on how quickly you're moving. Time flows differently depending on whether you're beside a very large mass, whether it be a pyramid or a black hole. This is to do with the way that gravity warps the time and space that Einstein imagined the universe to be. Now, this doesn't affect us very often at an everyday level, but it does affect us occasionally. The satellites that feed information into my smartphone do so having been corrected because of their rate of flow of time in orbit is different to the rate of flow of time that you and I are experiencing here. So we have experimentally verified it, but it leads to a situation where the universe becomes much more subtle, much more complicated, where those who are interested in science fiction have some grounds for talking about the difficulty of fully understanding time. Einstein went on and was helped by a number of other people who then began to ask the question, well, if time flows forward at different rates in this river, could you ever have a little eddy current where it flowed backwards? And time travel. And Kurt Gödel, a famous mathematician, said, actually, there's a solution to Einstein's equations, which says, yes, it's a possibility. If you set up a black hole and you rotate it in a certain kind of way and you send a spaceship in a particular type of way on a particular orbit, it's just possible that as that spaceship comes out from its orbit of the black hole, it's gone back in time. Now, that's mind-blowing. We've got to keep our heads on this in the sense that this isn't about the TARDIS going here, there and everywhere in time. It would be a particular way of time travel, but theoretically it's possible. And for me, that just says, again, wow, time is far more subtle, far more interesting, far more mysterious than we ever imagined it to be from our very limited experience here on planet Earth.
So one thing that comes up in sci-fi a lot is the difference between, say, moving very fast relative to another object or being in a greater gravitational field than another object. And the difference, I think, is actually quite profound in our experience of time, right? In one, when you're traveling faster than someone else, the experience is relative, but when you slow down again, you'll both have the same time on your watches, as I understand. But when we are subjected to a greater gravitational field than someone else, our experience or our difference of the differential in our experience of time is absolute. When you return to your friend, they will be older or younger depending on who's in the gravitational field. Can you explain a little bit about what could theoretically happen if we were subjected either to great speeds or to great gravitational fields?
Einstein talked about this in almost exactly those terms. He talked about a twin paradox, where I have a twin and one of us goes on a space journey. And if you accelerate me close to the speed of light in my spaceship, then you're exactly right. The rate of flow of my time slows down compared to back at Earth. Actually, what happens when you slow down doesn't recorrect that. That stays the same. So if I went on this long space journey and was accelerated close to the speed of light, it might be for me that my watch shows a year. I get back to the Earth and no longer is my twin alive, but time has been about 1,000 years while I've been away. But you're right in saying that there's a distinction between if I was to go on that journey and to circle a black hole, a very intense source of gravity. Well, I wouldn't want to do that, by the way, because the gravitational forces would rip me apart. It's a bit like spaghetti. But even if I did that, the rate of flow of time moves in a slightly different way. And yet the difference between what happens on Earth in terms of measuring time, what happens in the spaceship around the black hole, has a similar kind of effect. That I would arrive back and I would not be simultaneous with where I'd left. That is, again, I could be around that black hole for a year and come back and find 10,000 years have passed on the Earth. Now, trying to think about this in terms of everyday concepts of time is very difficult, because you rightly said our only experience of time is this linear flow of time which everyone shares. But the mathematics drove Einstein to believe that this was the case. And we've demonstrated experimentally that the mathematics is true on this. But it's what a writer called John Polkinghorne often talks about. It explodes the tyranny of common sense. We're dominated by our common sense notions of time here on the Earth. In fact, what science really says, and what science fiction writers rightly pick up on, is that don't be dominated by that tyranny. The universe is far more interesting and far more exciting.
Wow. I really like what you said about Newton and the urban myth that the apple fell on his head. Maybe it was a banana, I don't know. But what I love about that is that it was this, say that people like to think that there was this moment where he became fascinated with the effects of gravity, and that led him to believe that that there were some laws that maybe applied to the whole of existence of reality, these clockwork laws. Then Einstein, looking into it further, noticed some discrepancies. I think scientific discoveries are often inspired by a sense of fascination with the universe. And I'd ask the question, does the scientific endeavour merely open up more mystery?
Yes, it does. And there's a progressive sense in which you learn more about the universe, but then you're aware that there are other things as well. So Einstein succeeds Newton, and Einstein explains some of the things that Newton thought were true, and Einstein in effect gives a bigger theory to the one that Newton had. But in doing so, it allows us to see bigger questions. Now, of course, while Einstein was working on relativity, something else was happening, and that was the rise of quantum theory. And Einstein didn't like this at all. Newton and Einstein were people who believed that once you had a scientific law, everything was predictable. Although it may be subtle in terms of time, you could predict how time was going to flow around black holes. Quantum theory came along and said, hold on guys, you might explain the theory, but you can't predict the future. Now that was the next big step into mystery. It wasn't that the thing was subtle or flowing at different rates. It was actually, you couldn't predict the future. So we started with Newton's clock. You could understand it. That was Newton and Einstein understanding. And they thought then everything was predictable. But in fact, quantum theory and then chaos theory in recent years has said, you've got the law, you understand the law, you can write it on the back of an envelope, but that doesn't mean that you can necessarily predict the future. Now that's another sense in which time is subtle, in that you might understand how things happen, but you can't use that to predict the future, so the future is not written in stone.
That's fascinating, isn't it? That there you have, at the level of human experience, like Newton and Einstein, you see that the world is predictable. It's how we operate every day. When I wake up in the morning, I don't fly into the ceiling. I remain firmly on my bed because...
Most of the time, yes.
Well, most of the time. Yes, at one time a few years back. But this experience of the laws of the world being the same today and off into the future, I think is a very human thing. And so to Newton and Einstein, they could be forgiven for thinking that the world is predictable in that sense. So what do you think, David, are some examples of this unpredictability in our everyday lives?
Well, if I go back to cricket and the weather, this is a very important thing, because if Newton was sitting here, I should say to Newton, if I've got an understanding of the laws of the atmosphere, and if I've got a measurement of temperature and pressure at every point, and if I have a big enough computer, surely I can type in, what's the weather going to be like during the test match in Manchester in 3 years' time? And if Newton's right and Einstein's right with the way that the universe can be understood, why don't I get an answer back which says, on that day in Manchester it's going to rain, so don't book tickets for the test match? And the reason being is that in order to model the predictability of the weather, you need a computer bigger than the universe itself. Now that's a physical limit. You can't do it, and that's why the BBC doesn't try to do it in terms of predicting weather that far off. We're pretty good a day or two ahead, we know that. But once you get 7 days, 2 weeks out, that's very difficult. And this is a classic example of something where we know the laws of physics of the atmosphere. We've known them for 30, 40 years, but we still physically and theoretically can't predict. Other examples are really quite simple. The electronics that lies behind my smartphone, again, is based on quantum theory. It works beautifully. It allows me to use a smartphone in lots of different ways. But I fundamentally don't know how the electrons are moving in that smartphone. If I know how they're moving, I don't know where they are. And if I know where they are, I don't know how they're moving. That's called the uncertainty principle. So it's this bizarre thing where the theory mathematically works, but it's based on probabilities. Whereas at an everyday level, in order to catch a cricket ball, I need definite answers. I've got no chance of ever catching an electron because of this uncertainty over where it is and how it's moving.
What really interests me about this uncertainty is you mentioned that it wasn't just practically or physically uncertain, it was theoretically uncertain, which I think is a very different statement. So you were saying if you had a computer the size of the universe, maybe you could predict how the universe would progress, or even just how the weather on Earth would progress. And to me, that kind of indicates that maybe science could theoretically be used to predict and answer every single question we might ever have. But that theoretically unpredictable idea, I think that's substantially different, right? It's saying that even if we did have a computer the size of the universe that could theoretically predict all of these events, it still would not be able to.
And that's a crucial point, because many people come and they hear chaos theory and quantum theory and they say, well, let's leave it another 10 years. Let's leave it another 20 years. And then someday science will have worked this out. Whereas with chaos and the weather, that just is not possible. We understand everything. It's not as if we're going to understand more. It's just that we don't have the computational power to predict the future, and we never will be able to. Quantum theory alike, there have been one or two people, particularly a man called David Bohm, who used to say, well, maybe there's some kind of deeper theory to quantum theory which might get over this uncertainty thing. And for the past 100 years we've been looking at that, and still no one's found anything that will allow us to do that. So it may be, as most physicists recognize, uncertainty's just part of reality. Now that doesn't mean, and you were right earlier to say, that things aren't intelligible to us. Uncertainty is not about unintelligibility. Uncertainty is how we predict the future. Intelligibility is how we understand the systems of the universe. And the more that we've gone into science, the surprising thing is just how intelligible the universe is to us, that we can understand the laws. And not only are they beautiful and simple and elegant, they're also comprehensible for us. Einstein said the most incomprehensible thing about the universe is that it's comprehensible, that we can actually understand it. But understanding doesn't mean that we know everything about everything.
It seems as we're talking, it just seems patently obvious that the mystery is a fundamental part of our universe. As we were saying before, as we discover more, we realise that we know less, right? Which is fascinating. And I think, I don't want to do down the role of mystery. Actually, it seems to be the very driver for the human endeavour. It seems to be the driver for scientific exploration. But to me, I think we can very often be unsatisfied. When we see a mystery, it leads us to dissatisfaction. I want to understand it. And I think that driver it doesn't seem to be misplaced. As you're saying, they're intelligible and we can find out more. But I think it's led us to the point perhaps where we have to be confident with the unpredictability of the universe. There are many times, it seems, in our history where we've said we understand the universe completely. We understand exactly how it works. We don't think there's anything more to be discovered. Science or other subjects seem to stagnate, and then suddenly something new is discovered. Do you think mystery is here to stay?
Oh, absolutely. But there's different types of mystery. So there's that mystery where, in a sense, because of our computational power, we may never be able to give an absolute full prediction of the future. And that's just the way it is. I think then there's mystery in terms of those questions that science opens for us, but doesn't actually, at the moment, give us any answers. So one of the things that we know is that the universe is probably 95% made up of things called dark matter and dark energy. As a cosmologist, I only know what 5% of the universe is made of. The other 95%, I have no idea. But at least I know that I don't have any idea what the 95% is. Now, that drives me to say, I'm not going to simply sit back and say, well, 95%, that's a big task. I'm not going to think about that. Actually, what drives me is to say, I want to know what these things are. So there's that sense of mystery. But then I think there's a third form of mystery, which is where science is dependent on certain philosophical or metaphysical assumptions that goes beyond science itself. So, for example, where do the laws of physics come from? Why are they intelligible? Why are they elegant? Why are they beautiful? Why are they simple? Now, science assumes the laws of physics, doesn't explain where they come from. That's what we call a metaphysical or a philosophical or even a theological question. But again, that drives me to an answer, to try and find an answer. There's part of me which simply doesn't want to sit back and say, well, fascinating, isn't it, that the laws of physics are intelligible? I want to know, why are they intelligible? And many of the physicists who I work with, who come from a range of religious and philosophical backgrounds, we all share this one sense of, why are the laws intelligible? And that drives me again to keep asking the question. I don't want to hide behind mystery. If it's there and it's a real mystery, I have to accept it. But most of the time, mystery is a driving force where science keeps asking the questions.
I really like that. And the way in which you've written about this before, especially in commenting on Hawking's book, Brief History of Time, you kind of mentioned the idea that his way of thinking seems to almost conquer these metaphysical questions, right? Is the conclusion of his book sounds quite philosophical. And in fact, the whole time when you read his book, it doesn't have the feeling of simply a scientific journal. It has the feeling of a metaphysical book. It's trying to explore much deeper questions. Do you think that his way of thinking is something that we should embrace? Is it something that embraces mystery, or is it something that diminishes mystery in the universe?
I have a very high regard for Professor Hawking. It's interesting, in Brief History of Time, he is spurred into his work on the early universe because he went to a conference at the Vatican where he felt the Pope say, don't let science get involved in the very first moment of the universe. That's not for science. And although the Pope didn't actually say that, if you look at the records, Hawking heard that. And that became a driver for him to say, why not? Why shouldn't science give us an explanation of the initial conditions and the evolution of the universe? Now, I'm very with him on that. We would differ in terms of our religious interpretations. But I think saying, let's fill in the very first moment of the story of science, which is T equals 0 in terms of the Big Bang, I think is a possibility. Now, in 1987, when he published A Brief History of Time, he said that he'd solve it in about 10 years or so. Well, he wasn't able to do that. It's taken us a long time, and we're still working on it, still trying to understand the very first moment of the universe's history and how quantum theory and relativity can be brought together into one theory. I hope one day that will happen. But I may need to be patient about it. And it might be not string theory or M theory or some of the theories that are around at the moment to do that. It might be something quite startling. I suspect it'll be something even more simple, even more beautiful, even more elegant than we ever imagined to see. And in that sense, I think Hawking and others point the way forward to say, let's just not accept gaps in our scientific knowledge if we can keep asking questions about them. It's important for the human spirit, I think, to do that. I think it's important for our civilization to be curious about these questions. And I think it's part of the religious impulse, the gift given to us to ask these questions and to try and find out answers.
Yeah, David, I just love the passion that you speak with when you talk about this subject. And I really love this beauty that you see, or in your words, elegance of moving from a place of mystery and seeing the complexity, the enormous complexity of our world, and being able to derive simple and elegant solutions to that. I think that's a really profound impulse, and it seems to me that the very impulse that drives many of us, the human endeavour, it seems like our desire to understand and be able to reduce things down to an elegant solution. The fact that we believe those solutions exist, I find very interesting, and then the fact that we actually find those solutions is perhaps even more profound. It's not just a false desire. It's something real and something that we can actually engage with.
Absolutely right. Now, we have to be real about this. Most of science, our experience as scientists, is not about beauty and elegance. It's about boredom and disappointment and experiments that don't work and research councils don't give you enough money and peer-reviewed journals who don't see the brilliance of your work and postgraduate students who don't do what they tell them to do. And all of this is then wrapped around those moments that are often called wow moments, where you just see that elegance and beauty poking its head through the complexity and the failure and the frustration of the day-to-day work of science. Now, sometimes it seems to me, and this is true in science as well as in other subjects, we simplify too much the answer rather than looking for the simple answer. And that's a difference. When we try and make things in our own image, when we try and construct solutions that give an easy answer to questions such as suffering, for example, I think that's not looking for the simplicity and elegance and beauty at the heart of the universe. That's just laziness on our part. And when we peddle those answers as, oh, believe in this and all will be well and all the rest of it, scientists have done that in the past, just like everyone else. But the thing about science is that it keeps surprising us with just how beautiful the laws of physics in themselves are. Now, again, we need to keep this in context because there's much in the universe which isn't beautiful. There's much which is disordered, which is about entropy, which is about decay. But right at the heart of everything is a set of very beautiful equations. Now that excites me as a scientist. It gives me hope as a scientist. It encourages me to go on as a scientist. It gives me the energy to persevere through all of the difficulty of science. And when I read popular science or another scientist's work, I'm amazed at just what they've discovered about this universe.
I love what you were saying about wow moments there, and it seems in many ways that time, Einstein's equations of relativity, show us just how incredible the universe is, and these science fiction concepts which use his laws to create these unimaginable stories about time travel and seeing aging happening over a very short space. These are wow moments for us, aren't they? They're where we get to step out of perhaps the everyday and for a moment see something that's truly incredible, truly mind-blowing. And the question for me is not whether we can fully grasp how time works, but whether we could even begin to understand it without that mystery, without that beauty. Thank you, David, so much for being here today. It's been really, really cool to hear all of your ideas and explore just how nutty time can be. And thank you so much for joining us. This is the last in our series on time. If you want to catch the other two on memory and entropy, or if you want to catch our first series on AI, you can get them on social media, Facebook, YouTube, Instagram, the normal lot. See you guys soon.